Okay, so this first problem I'm going to do here is going to solve for electric force. Now, it's similar to electric field, so the only difference is the equation that we're going to use to solve for it, and there's usually a missing charge when we solve for electric field. But let's solve this question. The question is find the force on Q3, and let's see, let me get my mouse over here. So we're looking for the force on Q3, so what is the force right here? And what is the force basically from these two charges? So our force is demonstrated with this equation, Q1, Q2 over R squared, for any point charge system. So what I'm going to do to solve this is to first kind of analyze the charge distribution just to see what's going on here in terms of each charge acting on this charge right here. And then I'll actually calculate the magnitude of the force electric. And then, as always, when we have forces, we'll combine the x and y values to find the total or resultant force and find the official force here on this charge 3. So the first thing I'm going to do, and I guess I'll do it in color, is mentally kind of figure out what charge 1 is going to do to charge 3. Let's ignore all the effects of charge 2 and just look at charge 1. Charge 1 is positive, charge 3 is positive, so this is going to be a push away, like that, F. And I'm going to call this the force of 1 onto 3, so force of 1 onto 3. And this will be the radius, or the distance of 1 onto 3 right here, this 5 meters. And again, the reason why it's pointing away is because these are both like charges, so if this were free to move, and this was fixed, this would actually move away from it. So that's why it's pointing like that. Now I'm going to do the same analysis on Q2. I'm going to ignore Q1, pretend it's gone, and do the same thing. Now, if this were fixed and this were allowed to move, it would move toward the negative charge because they're oppositely charged. So this is what I'm going to do here, and call this the force of 2 onto 3. So this green is the force of 2 onto 3. This is the force of 1 onto 3. And since we got two forces pulling on our system right here, what we're going to do is find how much force total is going to act on this. Or in other words, really, which way is this thing being pushed in the end? And, you know, just based on our drawing, it looks like some of this x is going to be canceled by this. So I'm going to predict that's going to do something like this as the final. So this is the force total, if you will. And that's just a prediction. I'm not sure what's going to happen. Now notice that it's also up. I made, said it was up. It probably is going to be the same magnitude of this. So this is exaggerated. But that's the idea. So we're looking for this value right here. So my next step is to find the magnitude of this force. So force of 1, 3. This is going to be K. Charge of 1, charge of 3, between the distance of those two, like that. So K is our 8.99 times 10 to the positive 9 newtons meters squared over Coulombs squared, and that's our constant. Now Q1 is going to be our value right here, which happens to be 6 nanocoulombs. So nano is to the negative 9th, so I'm going to immediately convert that into regular coulombs. And then charge 3 is 5 nanocoulombs, like this. Oops, 9C. All divided by 5 meters squared, because that's the distance between these two charges. And notice that we're using the straight line distance, so it happens to give us that value, which is really nice. So when we solve for this, force of 1, 3, once we add that in our, put that into our calculator, I get 1.0, and I'm going to round here, 8 times 10 to the negative 8 newtons, like that. So I have the value of this force. I have this part of our triangle right here. I don't have my x and y just yet. So what I can do is I kind of take this out of the problem. And I'll keep working on this system. I have this part of our triangle. And what I need to do is actually break this down into its vector components of its x component and its y component. So what you see here is I have the hypotenuse here, and I'm looking for the x, or the projection onto x and the projection onto y of this. What I don't have is this angle right here, because I could use trig. So unless it's given to you, and sometimes problems are nice, they'll give that value to you. If not, what we can do is figure it out. If you notice that this is alternate interior angle, so the angle here is going to be equal to the angle here. Or in other words, if I do, if this is my y and this is my x, if I do tan, inverse tan of y over x, I can get the angle of this system. So that's 3 divided by 4, inverse tan. I get my angle as, I'm going to round it to 37 degrees right here. And that's by doing, I'll show you the numbers, inverse tan of my y, which was 3 meters, over the x, which was 4. So this is 37 degrees right here. Now I could carry out my calculations for finding x and y. My force 1, 3 in the x, due to trig, would be the hypotenuse of the triangle, which happens to be the value of this, times cosine of our angle. And then similarly, my y component is going to be the hypotenuse times sine of the angle, like that. So when I add this, or not add, but multiply, I'm going to use my hypotenuse, which is this value, 1.08 to the negative 8th newtons, times cosine of the angle. Okay, so I ran out of space, that's okay. But if I do this number times cosine 37, I get the value of the x force of this guy, and it's 8.62 times 10 to the negative 9th newtons. And I'll move these out of the way so it's a little easier to read, kind of squishing things here. So if I do the same thing but with sine, I get this value. .5 roughly times 10 to the negative 9th newtons. So what did I just solve for? I have my x and y components that make up this triangle right here. As such, I have my x here and I have my y. Now let's look at the triangle. I have my x going to the right, so this is positive. And then I have my arrow going up, which makes it positive. So both of these will stay positive like this. So what I'm going to do is follow the same exact process for f of 2 onto 3. So let me just do that. Let me put some space down below here. So f of 2 onto 3, it's going to be, the magnitude would be k q2 q3 over r23 squared. Now the r23 just represents the distance between those 2 points. So we have that distance. Let me raise it up a little bit just so you can see. The distance between these 2 points in a straight line is this 4 meters. So this is r23, like that. So if I set this up much the same way, I get 8.99 to the 9th newtons meters squared coulombs squared. Q2, I have to look that up, I don't remember what that was, so give me a second. Negative 2 nanocoulombs. So what I'm going to do is ignore the negative sign. I just want the value of it. I've already taken into consideration the direction, so I don't need to really put that in right now. Just the magnitude, meaning just the the absolute value. And then up, as you can see, I put in Q2, Q3, and then this is the distance of the 2 of them squared. So if I enter that into my calculator, take me a second. .74 times 10 to the negative 9th newtons. Now what I just solved for, by the way, just so you know, is if you look at this diagram up here, you can see I solved for the magnitude of this arrow. And this problem is really nice because we don't have an angle with this. This goes straight to the left, which signifies that I don't need to do any sort of trig because I don't have a triangle. So what F23 is, actually, if I look at the x and y components, we will have the following: x23 and x23, f23x, f23y. Well, it's all the way to the left, so we say negative because it's going to the left. And then it's the whole thing is going that way, so the whole magnitude goes there. Which makes our y very easy because our y, since there's no up component or down component, is 0. So we have the value, and again, this is this arrow that we're looking at in the diagram, like that. So, F total, we need to find the F total x and the F total y, and then we can find F total. F total x is going to be the sum of the x's. So what I'm going to do is just raise this a little bit just so we can see the other x's. There we go. So the first, the first x we had was from the previous problem, 8.62 to the -9th, plus the x of this one. Now it's going opposite, so it's going to cancel some of that, which is fine. We can do that, as it shall. And we'll get a value for that. Now the y's, this is up or positive, so 6.5 times 10 to the -9th newtons. And then we're going to add the y component of the second one. And yes, it's 0. I'm being very obvious here by doing that like that. So let me calculate this value. I get 1.88 times 10 to the -9th when I add those two together. And this is naturally just the same value since we're adding to 0. What did we just find? The x and y of our new triangle. They happen to both be positive, and then we see that the y is pretty high, so we have something like this. We have a small x and a large y. This represents this part of the triangle. Oops, sorry. No, it doesn't, because that's the... Let's go back. Oops, too far, right? Okay. The time's going to end. I'm going to try to do this very quickly. This is the 6.5 to the -9th. And this piece is the 1.88 to the -9th. And F total, what we're trying to find is the combination of these two forces, which is this. And as you can see, it's going to be to find the F total, we're using trig, so we're using the hypotenuse of the triangle, so F total is going to be set up like this. Take the Fx total squared plus Fy total squared. And then to find the angle, we could use the inverse tangent of the y's over the x. So I'm doing this because I might run out of time here. Like that. So I think I can enter in this really quickly before the time goes out. So I'm entering in the x component squared plus the y component squared into my calculator. Square root. I get 6.76 times 10 to the -9th newtons, and the angle, I'm going to do the y, which is the 6.5 to the 9th, divided by the 1.88 to the 9th, inverse tan it, and I get 73 degrees. So that's our force, would be 6.7 to the -9th at 73 degrees, which makes sense because this is a pretty steep angle right here. So that's how you'll do a Coulomb's law type of problem.